So we're going to be talking about the second law of thermodynamics in this series of lectures. So the second law of thermodynamics came about because people observed that the first law of thermodynamics could be followed in certain situations, but those situations didn't occur. Recall that the first law of thermodynamics basically states that energy must be conserved. Energy has to go somewhere. If you do work on an object, it can gain heat or interior energy, or you add heat to an object, its internal energy can increase. Or if heat leaves an object or the object does work, then its internal energy decreases. So why, as long as energy is conserved, if I set a hot cup of coffee on a counter, why can't the coffee get hotter? If it takes energy from its surroundings, if the surroundings get cooler, my cup of coffee could get hotter and it wouldn't violate the first law of thermodynamics. Well, it turns out that energy and heat usually only goes in one direction. So we have to learn about reversible and irreversible processes. A reversible process is just a process by which you can easily reverse the situation. So imagine taking a balloon, an inflated balloon, and squeezing it slightly. As you apply pressure on the outside of the balloon, you can increase slightly the temperature in the interior gas or the pressure in the gas interior by decreasing the volume. So by squeezing the balloon, you can change the state of the gas inside, but then when you relax and let the balloon go, it goes back to its previous temperature and pressure, temperature, volume, and pressure. So that is a reversible process. Picking up a book, putting it on a shelf, and then taking that book off the shelf and putting it back on the ground at the same location is an easily reversible process. But most processes are not easily reversible. An example of an irreversible process is popping a balloon, right? If I pop a balloon, I break the rubber on the balloon, the gases are escaped. There's no easy way to put those gases back into a sealed balloon, the same sealed balloon, because not only is the balloon destroyed, the gases have escaped. Irreversible process, breaking a dish, right? I can knock a coffee cup off a shelf, it shatters on the floor. Now, there's no easy way to put that back together. So those are examples of irreversible processes. And heat transfer is typically an irreversible process. Heat goes from hot objects to cold objects. So if you have that hot cup of coffee sitting on your kitchen counter, the heat from that hot cup of coffee is transmitted into the air around the mug, is translated into the counter itself from direct contact through conductivity with the countertop. And if you come back a few hours later, that coffee mug has reached room temperature. It's reached the same temperature as its surroundings. The heat has transferred out of that coffee mug. That is an irreversible process. No matter how long you leave that coffee mug alone, the heat will not come back in and give you a hot cup of coffee. Likewise, if you place a cold ice drink on the countertop, cold beverage, iced tea or whatever, the heat from the surroundings will go into that iced tea, melting the ice, bringing the ice up to room temperature. And then come back a few hours later, you have, again, a room temperature beverage. But in that situation, the heat goes into the system. The environmental heat goes into the iced tea, whereas in the coffee, the heat of the coffee came out into the environment. Heat transfers in one direction, from hot objects to cold objects. That's spontaneous. That happens just by waiting with time. It never spontaneously does the opposite. It never goes from a cold object into a hot object. You do not put a hot cup of coffee in the freezer, come back later, and the coffee is now boiling and the rest of the freezer is cold, even colder than it was before. That wouldn't violate conservation of energy as long as you balanced, you had the same amount of heat going into the coffee as you had removed from the freezer, but it clearly violates the second law of thermodynamics. And the second law of thermodynamics, not only can heat transfer from hot to cold objects, you can use that spontaneous process to actually do work. And the device used to pull work out of the transfer of heat from a hot object to a cool object, or a hot environment to a cool environment, is called a heat engine. A heat engine is a device that pulls heat from a high temperature reservoir and does work with that, depositing any remaining waste heat into a low temperature reservoir. The typical example of this is a steam engine or your automobile engine, right? Fuel is injected into a cylinder and ignited, causing a huge temperature increase. That expanding gas, the heat released from that expanding, exploding gas, is used to drive a piston, so work is being done, and then the remaining spent hot gas after the piston is expanded is dumped through the exhaust system into the air outside. So, for a heat engine to work, you need a high temperature reservoir and you need a low temperature reservoir. So, without that temperature difference, heat engines don't work. You're taking advantage of the fact that heat spontaneously wants to go from high temperature to low temperature. So QH is the amount of heat pulled from the high temperature reservoir. That's, again, measured in joules. That total amount of heat, some of it goes off to do work, and the remaining bit that doesn't do work is dumped into the low temperature reservoir, overall increasing the temperature, right? But usually on a very small scale. So the automobile exhaust that gets dumped out really does not increase the temperature of the atmosphere substantially, because the atmosphere is so great. So to figure out how much work is done, we need to calculate how much heat did you pull from the hot reservoir and how much heat was dumped into the low temperature reservoir. Now, ideally, you would think, well, why can't I just pull all the heat and do work with it? Well, we'll find out when we talk about an ideal engine, that's not possible. It is not possible to have no heat dumped into a low temperature reservoir. If it was, basically entropy, and we'll learn about entropy in a bit, would never be zero. I mean, entropy would always be zero. You could take an object of some temperature, a hot object, pull all of the heat from that object till it's absolute zero, get all the work done out of that object, and it would violate the second law of thermodynamics. So we cannot have a low temperature reservoir that does not accept some waste heat. So how do we calculate the efficiency of a heat engine? Well, efficiency is basically what do you get versus what do you pay for. Well, what you get is work out of the engine. What you pay for is the amount of heat you draw from the hot reservoir. Well, we have the equation for work up here. It's the difference between the heats in the hot and low reservoir. Plug that in here. Distribute the QH, right? QH over QH is 1 minus QL over QH gives us the efficiency of a heat engine. This is in general terms. This applies to all heat engines. If you know how much heat you're pulling from the low temperature reservoir or dumping into the low temperature reservoir, if you know how much heat you're pulling from the high temperature reservoir, you can calculate the efficiency of that engine. Now the efficiency has to be between 0 and 1. Right? If the low temperature and high temperature heat are the same, basically if you're taking all the heat from the high temperature reservoir and dumping it in the low temperature reservoir, none of it is used for work. The efficiency 1 over 1, if this is the same, this becomes 1. 1 minus 1 is 0. The efficiency of the engine is 0. If you could not have all of the heat from the hot reservoir go into work, then the efficiency would be equal to 1. The engine would be 100% efficient. And we'll see that that's just not possible. There is a maximum theoretical efficiency that we can get from these types of heat engines. And the heat engine we will look at specifically for this is called a Carnot engine. So we're going to look at Carnot engines. These are ideal heat engines because they employ reversible processes throughout the entire cycle of the engine. So to look at this cycle, we're going to look at a PV diagram, which we've studied in earlier chapters, so pressure versus volume. Now there are 2 dotted lines shown here, and this figure is also in your text. 2 dotted lines showing isothermal lines. So if you are on one of these dotted lines, you have constant temperature. So T sub L, the temperature of the lower reservoir, is shown at the bottom dotted line. T sub H is shown above. So the process, the Carnot engine process, starts at point A, goes through an isothermal process, decreasing the pressure, increasing the volume to point B. So A to B is isothermal, that means constant temperature. B to C is an adiabatic process, that means constant energy. So you can see the temperature changes. Not only does the pressure change in the volume, the temperature goes from TH to TL. Then C to D is another isothermal process, staying on the same temperature T sub L, decreasing the volume, increasing the pressure slightly. And then finally D to A is adiabatic, again, constant energy. So in this situation, the volume underneath a PV diagram is the work done by that process. So the work done, the process A to B releases heat. Q sub H, this is an isothermal process, not an adiabatic one, so energy is not conserved. Heat is transported into the system from some external source. Q sub H is added to the system. B to C is adiabatic, that means no energy enters or leaves the system during that process, no heat, therefore enters or leaves during that process. C to D is again isothermal, so energy is lost, Q sub L leaves the system, that's the energy dumped. And then D to A is an adiabatic process, again constant energy, the energy doesn't change. So the work inside this diagram is the work done by the engine. Integrate this from A to B and then subtract the integral from C to D. So that gives you the work done by this engine. Heat from the hot reservoir enters the system, heat leaves the system, dumped into the cold reservoir. So again, we have two isothermal processes and two adiabatic processes. For isothermal processes, last chapter, you learned that the work done, in this case, the heat added to the system, is equal to number of moles of the system times the gas constant times the temperature of the system. For QH, the temperature through this whole process is T sub H. It stays on that line. Times the natural log of the volume at point B divided by the volume at point A. You can see the volume at B is greater than the volume at A. So that's the heat added to the system. For this lower isothermal process, the heat leaving the system, it's the same equation now, except now the temperature is that of the low reservoir, and you're integrating, the natural log is points C and D. So going back to a previous equation on efficiency, efficiency is 1 minus the heat dumped into the low temperature reservoir over the heat pulled from the high temperature reservoir. Plugging in the equations above, N cancels, R cancels. So we end up with T sub L over T sub H, 1 minus T sub L over T sub H times the natural log of VB over VA divided by the natural log of VC divided by VD, the volume, the ratio of the volumes. All right. Let's look at these types of processes. Going over here, for adiabatic processes, you learn that the pressure times the volume is raised to some gamma function. For gases, that depends on the degrees of freedom of the gas. It could be, you have to look up what process it is to figure out what gamma is. This is equal to a constant, though. So the pressure and the volume at points B raised to the gamma is equal to the pressure times the volume at point C raised to the gamma. And likewise, D and A are set equal to each other. And then from the ideal gas law, PV equals nRT. N doesn't change. The number of moles of gas stays the same. R stays the same. So you can come up with this ratio, these ratios for the ideal gas law, because these occur for these adiabatic processes, for these isothermal processes. Your book goes through the math. It's a full page derivation. You can show using these equations, I won't do it on the board here, but you can follow along in your book if you'd like. you can show using these equations that the volume ratio VB over VA is equal to the volume ratio VC over VD. And since, therefore, these ratios are the same, it's the same logarithm on the top and the bottom, so that logarithm is equal to 1. That ratio of logarithms is equal to 1. The efficiency reduces down simply to 1 minus the temperature of the low temperature reservoir, sorry, not CL, temperature of the low temperature reservoir divided by the temperature in the high temperature reservoir. These are not delta T's, these are T's, so they must be in Kelvin. This efficiency equation only works if the temperatures are in Kelvin. If you use any other temperature, Celsius, Fahrenheit, whatever, you will get a wrong answer. This shows you the efficiency, maximum possible efficiency of a heat engine operating between those two temperature reservoirs. And of course, if the temperature reservoirs are the same, this ratio becomes 1, 1 minus 1 is 0, the heat engine will not work. It has a 0% efficiency. The efficiency can never be 1. For the efficiency to be 1, the low temperature reservoir would have to be at absolute 0, which of course doesn't happen in the real world, or the high temperature reservoir would have to be infinitely hot, which again doesn't happen in the real world. So the efficiency, this gives you the maximum possible efficiency an engine can operate between those temperatures. All real engines operate at lower efficiency than a Carnot engine. The Carnot tells you the ideal, the best that you can do between those temperatures. All real engines are worse than that. So typical Carnot efficiencies for like engines like in your car, 30-40% at best, absolutely at best. And real engine efficiencies are much lower. So this is a Carnot engine, the very best that you can do. And your book talks about the Otto cycle, which I won't get into. That's a more realistic type of an engine, which will have a lower efficiency. However, heat engines aren't the only type of process that we can look at in this section, this thermodynamics. We can also talk about what if we want to do the opposite? What if we want to take heat from a low temperature reservoir and dump it into a high temperature reservoir? According to the second law of thermodynamics, this cannot happen spontaneously, but we can force it to happen. And we force it to happen through a process called a heat pump. The second law of thermodynamics states that heat does not spontaneously move from a cold reservoir into a hot reservoir. But what if you wanted to? What if you want to remove heat from a cold reservoir and dump it into a hot reservoir? For example, a freezer or a refrigerator, where you want to take energy or heat, pull it out of the icebox and dump it into the kitchen, right? The idea is to make the icebox colder, and then the consequence is to make the kitchen a bit warmer. That doesn't violate the law of conservation of energy. The energy still goes somewhere, but it can't happen spontaneously. So how do you get it to happen? Well, you do it by doing work on the system. So we want to, our low temperature reservoir, imagine this is the inside of your house that you're air conditioning or the inside of your refrigerator. You want to pull heat from that system, Q sub L, and you want to dump that heat into your high temperature reservoir. In this case, the high temperature reservoir would be outside on a hot day, or the kitchen air or surrounding your refrigerator. To do that, you must put work into the system. So what ends up happening is you do work on the system, a small amount of heat is pulled out of the low temperature reservoir, they combine, the work and the Q sub L, the heat from the low temperature reservoir combine, that combined heat is dumped into the high temperature reservoir. So you're actually generating more heat than you're removing from the low temperature reservoir, which is why if you just open your refrigerator and leave it running, it will try to cool the box, but it will be dumping more heat into your kitchen than the cold air will be generated inside the box flowing into your kitchen. So by opening your refrigerator, you might think, oh, it'll just be neutral, or turning on an air conditioner sitting in the middle of a room. You're like, oh, it's trying to cool the air, but it also warms the air, so the warm air is expelled out the back, so they'll balance one another. And the answer is no, you'll actually put more heat into the system, more heat into the environment than you pull out. So Q sub H, the amount of heat you dump in the high temperature reservoir, is the work plus the heat you pulled from the low temperature reservoir. So solving this, work is the difference in the temperatures. For a heat pump, you don't talk in terms of efficiency. You talk in terms of what's called the coefficient of performance. How much heat can you pull from the low temperature reservoir for a given unit of work? If you can pull 10 joules of heat from your refrigerator with 1 joule of work, then your coefficient of performance is 10. So the higher the coefficient of performance, the more efficient your heat pump or refrigerator is. Now, your book talks a little bit about the difference between coefficient of performance for a refrigerator and a heat pump, and I'll talk about that in a moment. For the sake of argument, let's pretend they're the same for now. So, plugging in the equation for work down there, you get Q sub L, the coefficient of performance is equal to Q sub L over the difference in the heat, Q sub H minus Q sub L. Again, this equation holds for all refrigerators, air conditioners, and so on. This is generally true. If you want to know what the ideal coefficient of performance is, you can replace, as we did before, Q sub L with T sub L, Q sub H with T sub H, again, assuming temperatures are in Kelvin, and you can come up with an ideal coefficient of performance for a refrigerator. The coefficient of performance should be on most refrigerators. They'll tell you what the coefficient of performance is. Sometimes it's a K value, sometimes it's COP. You can, of course, pick the refrigerator with the best coefficient of performance, the most efficient refrigerator. But the basic principle of how a refrigerator works is, again, heat doesn't spontaneously go from cold to hot. What a refrigerator does is it takes gas from inside, or coolant from inside a closed system, and it expands this coolant, like Freon, for instance, which isn't used anymore, but let's pretend that it is, or rarely used. Freon expands. When a gas expands, it cools off. You probably all experienced an aerosol can. When you spray the aerosol can, the can gets cold. So the Freon expands, gets very cold, and then that tubing is basically mixed with a fan blows the refrigerator air over that cold tubing, cooling off the air inside the refrigerator. The warm heat energy, right? So the Freon that's going through the fridge, inside the fridge, is colder than the air inside the fridge. So heat is transferring from the warmer air to the colder Freon. Heat is spontaneously going in that direction. But that follows the first and second laws of thermodynamics. Now, what your refrigerator does is it takes that warm Freon, it compresses it, makes it very warm. Think of it as hot Freon now. And it pumps that hot Freon behind the grating in your refrigerator or in the vents of your air conditioner. It gets a closed system, but it pumps it through those metal vents, heating up those metal vents. And then the heat from those hot metal vents then interacts with the air outside. And if the air outside is cooler, the heat transfers from that warm Freon, the air conditioner, to the cooler air outside, cooling off that hot Freon, which is then goes back inside the fridge, expands, dramatically cools off, and again takes heat from the interior air of the fridge into the Freon. So in both cases, heat spontaneously flows from hot to cold. It's just that a compressor needs to do work to take that warm Freon, compress it down to make it hot, allowing it to be pumped through the back of the fridge, allowing the heat to transfer from the hot Freon to the cooler air outside or in your kitchen, depending if it's an air conditioner or a refrigerator. So this is basically how air conditioner or refrigerator works. That's the work that's being done as the compressor, right? You have to plug in a refrigerator for it to work. It won't work spontaneously. Now your book gets a little pedantic and it talks about heat pumps. It says, well, technically a heat pump, the idea of a heat pump is it takes cool air outside, pulls heat from it, and dumps it into your house. So the coefficient of performance for a heat pump is technically Q sub H over the work done, not Q sub L. Because in a refrigerator, you're removing heat from a cold reservoir and you're dumping it it's waste heat you're dumping. Whereas for a heat pump, technically, you're pulling heat from a cold reservoir. That's the heat you want, right? So this coefficient of performance for a refrigerator talks about how efficient a refrigerator is at pulling heat from the low temperature reservoir, which is what you want a fridge to do. A coefficient of performance for a heat pump talks about how efficiently it can pull heat into your house, right? Plus the work done. But remember the high temperature reservoir includes the work done. So the bigger the work done, this also increases Q sub H. Whereas if you increase the work here, your coefficient of performance will drop. So it's a little pedantic, but there's a slight difference between the coefficient of performance for a refrigerator ideal and a heat pump. But just a reminder, what trips most students up, in my opinion, in my experience, is the fact that if you don't use Kelvin for temperature, you will get the wrong answer. Now finally we come to the idea of entropy. Now entropy is a measure of the order, or rather disorder, of a system. So think of it as entropy as just measuring how messy a system is, how disordered or disorganized it is. It's a way of quantifying the second law of thermodynamics. The second law, again, states that heat cannot go from a cold object to a hot object. Another way of talking about the second order is every time heat is transferred, a small amount of it becomes unusable. Think of the heat engine. All of the heat you pull from a hot reservoir cannot go into work. Some small amount of heat must be dumped into a cold reservoir. That is increasing the entropy or disorder of that low temperature reservoir. So entropy, or the change in entropy, S. Entropy is a state variable. So that means that at a given pressure, temperature, number of molecules, and so on, a system will have the same entropy. So if you look at the Carnot engine, at point A, whenever you come back to point A at the Carnot engine, you have the same entropy as when you started. The change in entropy is integral, the amount of change in heat over 1 over the temperature from states A to B. So again, think of that PV diagram. Pick two states, A and B. The change in entropy is 1 over T dQ. Now, if temperature is constant, if it's an isothermal process, of course you can pull the temperature out, but the temperature isn't always constant between states. And since it's a state variable, it's not affected by the processes by which you go from point A to point B. For example, if you have a PV diagram, you have state A here and you have state B down here. If you do an isothermal process, or you decide to do a constant pressure process and then a constant volume process to get to point B, the entropy change will be the same. The entropy at point B is a fixed value. The entropy at point A is a fixed value. This allows you to calculate what that entropy is. So sometimes it's easier to assume an isothermal process and calculate the change in heat that would be required to calculate how the entropy changes. This applies for reversible processes. Irreversible processes, the entropy goes up even more because you lose energy, you lose heat to turbulent flows. Now, in a system with completely reversible processes, like a Carnot engine, the change in entropy between the states is 0. If you go from state A back to state A, no entropy is lost, right, or gained. The entropy remains the same at those states for a reversible process system like a Carnot engine. If the system does not have reversible processes, entropy definitely increases. So entropy, this disorder of a system, never decreases. It either stays the same for reversible processes or it increases for irreversible processes. A simple example is a perfume bottle. Take a bottle of perfume or cologne in your room or in any room, open it up, and eventually you can smell the perfume or cologne in that room. The molecules that were nicely isolated in that container are now spread throughout the room. That is an irreversible process. You cannot easily gather up those scent molecules and shove them back in the bottle. And they certainly won't spontaneously go back in the bottle. So the entropy of the system and the environment increases with time. So since you can't use 100% of the heat to do work, that every time you transfer heat, a little bit of it is wasted. That means that eventually you'll run out of energy. You'll run out of useful energy. So what happens when you run out of useful energy? This is called heat death, the heat death of the universe. So since the entropy of an isolated system can never decrease, never become more ordered, it always increases and becomes more disordered, over time the universe, the entropy of the universe increases, constantly increasing, never decreasing, until eventually the entropy of the universe will reach a maximum value and no useful work can ever be done. We call this the heat death of the universe. Right now, sometimes the second law of thermodynamics, the concept of entropy, is incorrectly used to argue against the theory of evolution. The idea that how can evolution be true? Look at how complex human DNA is. How can a simple organism billions of years ago evolve into the complex organism we have today? That is an order, right? That's increasing the order system. It's not becoming more disordered, it's becoming more ordered. How is that possible? Well, Earth is not a closed system, right? The entropy, the change in entropy, delta S, depends on delta S, depends on the entropy, the change in entropy of a system, plus the change in entropy of the environment. The Earth has a huge amount of energy being dumped on it daily, right? The sun is dumping an enormous amount of energy on the Earth. The Earth is not a closed system. The Sun-Earth system can be considered closed, and that system is increasing in entropy. As the sun goes through nuclear fusion, it's taking energy mass, creating light with it, creating heat with it, creating a more disordered, disorganized form of energy, increasing the entropy of the system. So the common example of entropy is your room. It's not a great example, but it's a common example. Your room, right? Your room gets dirty with time. That's increasing entropy, increasing disorder. How do you decrease the entropy? You do work, right? You put in work to clean your room. But you might be like, well, that just decreased the entropy. You just said it couldn't decrease. Well, you used energy to clean your room. That went from a useful chemical energy of your body into motion kinetic energy, increasing the thermal energy of your muscles. You generate heat. You generate heat as you move things, friction, and so on. So you actually increase the entropy in total when you clean your room. So while the entropy might locally decrease in one part, it must increase somewhere else in a closed system. So the net change in entropy is either zero for reversible processes or it is increasing for irreversible processes.